problem involving a charge inside a cube, and we would like to illustrate how symmetry plays a very important role in being able to evaluate or use the Gauss's law in a easy manner. So let's draw the figure appropriate for this. So this represents a square, or maybe we can use, so that's a square. Let me get rid of that tiny small line there. So that's a square, and we have a charge right at the center. Let's say it's a positive charge, and the electric field lines due to that would be radiating outward. So this represents the electric field lines going out. We'll draw a few more lines just to give a feel for this. So that's your electric field lines. They're all outward. So if it was a negative charge, all these lines will be pointing inward. Uh, these are presently just lines. When I draw the arrows, that's what gives it a directional sense to this. It is corresponding to a field. Here, since it's a positive charge inside, all these field lines are, all these field lines are pointing outward. If it was a negative charge, it will be going inward. So that's represents your field lines. This is, of course, a cross section of the cube. The cube itself would look like this. That's how the cube would look like in three-dimensional image. And we are seeing it exactly from the top of one of the faces. In that way, you only see the square. So that's a representation of the cube, and the plane gives us a reasonable idea of the field lines. But this is spherical. The nice feature is, if you're interested in the flux, remember, is how much electric field is flowing through an area. And if we were to think of just the flux on face one, there are 6 faces to the cube. Let's say this is the face we are talking about, face one. And for concreteness, let's say this is X direction, that's your Y direction. And Z is coming out of the plane. We would like to calculate the flux through the first phase, and that's equal to, if we were to explicitly calculate this, the formula for this is phase one. So representation, this is area element. Break this area into tiny small area elements and dot it with the electric field at each point on the face. And we do see that the electric field lines are not uniform in this case. At this point, it is here. At this point, it is pointing slightly in a different direction. Here, it's horizontal, and then it starts going downward. So it's not uniform at all. In fact, dA elements, just to give a feel for this, this is dA at each point on this face. That's your dA. Right at the center, dA is parallel to the electric field line penetrating from that, but otherwise they're in general not. Right? And this is only showing a slice of the plane. So there is a whole plane which is protruding out in the z direction. And we have to calculate all these dAs, right? So this is A. All these area elements dotted with the corresponding electric field at each of those points. We have to split this plane into many tiny elements, and each of those elements we have to dot it with dA. And unlike in the simpler problems where if electric field was uniform, then it can come out of the integral, and then it is just the total area. But here we cannot. In fact, just to give you a feel for what this looks like and how tedious this could be. So let's say this is phase one, and this is two integrals, and we have what are we integrating on? We are integrating on y and z. So this is dy times dz, y dy and dz, because this plane that we're talking about, the phase one, that's an integration over y and z. I won't be really needing to do this integral, but I'm trying to illustrate how complicated this could be and how Gauss's law is going to simplify this whole calculation. So that's in the I hat direction. The area is all pointing in the x direction. So it is dA is, so I should write this down here. dA is dx times dy, and do dy times dz in the direction of I hat. That's my dA. Dotted with my electric field, which is area is neat, it's in the I direction, but electric field is kq over r square, but r square is x square plus y square plus z square. And then we need a direction to that. So it is, direction is x in the I hat direction, that's it, plus y in the j hat direction, plus z in the k hat direction. That's not a unit vector, so I have to divide it out by a unit vector again. So it's x squared plus y squared is the magnitude of that vector, and square root of it. That's your direction. The second fraction that I wrote is the direction of the electric field. So the flux passing through phase one is equal to the I hat dots only with I hat, and this zero everywhere else. So I have two integrals to do, dy, and let me see, it's two integrals, dy, dz. I hat dotted with I hat as one, and the integral I'm doing is kqx divided by, the note is x, the integral is over y and z, so x doesn't really care. X squared plus y squared plus z squared. Now that's 3 by 2. And this is on phase one, which means I'm setting x to be equal to, if it is 75 centimeter in edge length, and if I'm at the center of the cube on one side, I'm going 75 by 2 centimeters. So it's 75 by 2 centimeters. So that's what decides my phase. That's an integral we can do, and that's, so this is one way of proceeding. But I'm not going to do this. We are going to show that how this is going to get very simple without actually doing this integral. So the total flux in principle would be equal to phi 1 plus phi 2 plus 6 phases, and you have to do this for 6 phases. So first do this for phase 1, fix your x and integrate over y and z. For phase other phases, fix either x or y or z and integrate over the other quantities. That's how we could explicitly calculate the flux. But the idea here is that if it's a closed surface, so that's Gauss's law, makes it significantly simple. And Gauss's law tells us that this total flux, since the cube is a closed surface, this circle on the integral represents this is a closed surface. It doesn't matter what these integrals are, how much ever complicated these integrals are. This has a information about the source of the electric field, and the source of an electric field is a point charge. Either it could be a positive charge or a negative charge. If it's a positive charge, it's a source. If it's a negative charge, it's a sink. In this case, all the electric field lines are radiating outward, so it's a positive charge. Even if there was a sink, it doesn't matter. It's the total charge that comes in. So that's equal to the total charge enclosed, the sum of the charge enclosed, that's how you can see it, over epsilon naught. But we do know how many charges are enclosed. We are given that there's only single charge in there. So we immediately know what's the total flux. We don't have to calculate this integral. All this I was trying to illustrate how complicated it can be, but it is not. You use the right hand side of Gauss's law. So Gauss's law is this. Correct? So that's your Gauss's law. The total flux, the left hand side, is equal to the total charge. So phi total is simply the total charge, which is 105 microcoulomb divided by epsilon naught, which is 8.85 into 10 raised to minus 12. And epsilon naught is coulomb square over Newton meter square. If I invert this out, so I immediately get, without any not much work at all, right? I just have to divide a number. In fact, it is just scaled. So phi divided by 8.85, and that's 11.86. So it's 11.86. I should take off the extra digits. That's 10 raised to 6 Newton meter square over Coulomb square. That's only 3 sig digits, so that's 11.9 mega or 10 raised to 6 Newton meter square over. One of the Coulomb cancels out, right? So there's a Coulomb also here, so that's one of the Coulomb cancels out. So that's your total flux. That's actually part B of the problem. So this is part B. I will not, so this is not part A. The earlier whatever I was describing is to explain what how electric flux, if explicitly calculated, could be a complicated uh, or it could be a tedious work to do. Let's next do part A. Each of these phases have exactly the same amount of flux going through because of symmetry, right? So we can just see here that it doesn't really matter which phase you're doing, it's going to be the same area element that's going to be multiplying the electric fields at each point there. So it's A, and so that's dA, and that's dA. Which means that flux being a scalar, they're all the same. So if the charge is at the center, so the total flux is equal to 6 times the flux from a single phase. So the flux going through any one particular phase is simply the total flux divided by 6, and that's equal to, so that's again to two, 3 6 digits. That's 1.98 into 10 raised to 6 Newton meter square over coulomb. Like 11.9 divided by 6 is 1.98. But see, is this going to stay the same if you were to if you were to move the charge away from the center? So let me draw this again just to give a feel for this. So that's now where what our cube is, let's say. And if the charge was somewhere here, let's take the extreme uh, situation. Can be further extreme. Can move it further to the right, but uh, and let me draw the field lines now. And let's see your field lines. Let's see. And it's clear that on the left side of the on the left face uh, here, for completeness, let me draw a few more lines just to make all the lines that I've drawn up earlier short. Oops. It's clear that on the right side, since we are closer to the charge, the flux will be larger in magnitude, and on the left side, since we are away from the face, it would be weaker. So if we were to label this flux as 1, so this is our phase S1 and this is phase 2. It's expected that since the area is the same, the flux of phase 2 is not equal, at least not equal. We can even say the flux of phase 2 will be less than the flux on phase 1, but it's clearly not the same. So now we cannot really argue that it is 6 times phase 1. But even in this scenario, it is still the total flux remains the same. Total flux is equal to the total charge enclosed divided by epsilon naught, which is still 11.9 into 10 raised to 6 Newton meter square over coulomb. But the flux due to a single phase is not equal to the flux total divided by 6. So answer to part A uh, does change. We cannot actually now use symmetry, so we have to explicitly do it. But part B still remains simple. The total flux is going to be the same. So if the flux increases on the right face, it will decrease on the left face in such a way that the total remains the same. Hopefully this was useful illustration of electric flux. Let me stop the video here.